which is really about energy transformations. It's concerned with heat changes that occur during chemical reactions. Energy, capacity for doing work or supplying heat. Weightless, odorless, tasteless. If within the chemical substance, it's called chemical potential energy. Gasoline contains a significant amount of chemical potential energy. Of course, we use that to burn to power cars and engines. Heat, represented by Q, is energy that transfers from one object to another because of a temperature difference between them. Only the changes can be detected. So we really don't measure heat in itself. What we measure, the fact is that something is hotter than something else colder, and we can tell the difference between them, and that's how we judge the amount of heat, by the differences. Flows, of course, from warmer to cooler objects. Pretty much all chemical reactions and changes in physical state involve either a release of heat, exothermic, or an absorption of heat, endothermic. In studying heat changes, we need to think of two parts. The system, the part of the universe on which you focus your attention, and the surrounding includes everything else. Together, the system and surroundings constitute the universe. Thermochemistry is concerned with the flow of heat from either the system to its surroundings or the surroundings into the system. Conservation of energy states that in any chemical or physical process, energy is neither created nor destroyed, it's just transformed. All the energy is accounted for as work, stored energy, which should also be potential energy, or heat. Heat flowing into a system from its surroundings, defined as positive. Q will be positive. This is called endothermic. The system gains heat. The system gets warmer as the surroundings cool down. Heat flowing out of a system into its surroundings, defined as negative. Q has a negative value. This is called exothermic. The system loses heat, but the surroundings heat up. So imagine, for example, a fire. The system, the people gain heat from its surroundings, the fire. This is endothermic. Q is positive. You are absorbing the heat from the fire. On the other hand, the system, the body, cools as perspiration evaporates. The heat flows to the surroundings. This is exothermic. Now, again, you could think of that first one as being also exothermic in the sense of if you define the system as the fire itself, then it's putting its heat outward that you feel as part of the surroundings. But if the system is the people who are absorbing the heat, you get warmer by being near the fire, then that would be endothermic. So it's very important on how you describe what is it, where's your focus? What are you calling the system, and everything else becomes the surroundings. So people can warm up, that would be endothermic, or they can cool off by perspiring, and that's what the body does to cool off. That would be exothermic. And again, note, endothermic Q is positive, exothermic Q is negative. Every reaction has energy change associated with it. Exothermic reactions release energy, usually in the form of heat. Endothermic reactions absorb energy. Energy is stored in the bonds between the atoms. The last part where we talked about a catalyst and activation energy. Okay, part of the point is the energy stored in the bonds. So you got to break the bonds to then reform a different arrangement of the atoms. Okay, calorie defined as the quantity of heat needed to raise the temperature of 1 gram of pure water, 1 degree Celsius. Used except when referring to food. Notice capital C, calorie, written with a capital C, always refers to the energy in food. It's 1 kilocalorie or 1,000 little c calories. The calorie is also related to the joule, the SI unit for heat and energy, named after James Joule. 4.184 joules, or 4.2 if we round it, equals 1 calorie. Heat capacity, the amount of heat needed to increase the temperature of an object exactly 1 degrees. Since we're talking about an object, we would have to take into account the object's mass and its chemical composition. This is why I talk about the other day, it takes a lot more heat to warm up your pool than to warm up a glass of water. You would have to take in the mass to account for that. Specific heat is the amount of heat it takes to raise the temperature of 1 gram. So before we were talking about the whole object, now we're just talking about 1 gram of the substance by 1 degree. This is often called simply specific heat. Note table 17.1, page 508. Water has a huge value when it is compared to other chemicals. So here's your table. Notice water in its liquid form, 4.18 joules per gram. Solid, a little bit less. Notice that down there at the bottom when you have metals, how small those values are. So they heat up very quickly. They also cool off very quickly. Water's value is very high, so it takes a lot of energy to warm water up. It also takes a while for the water to warm down, to cool down. Again, it can be 4.18 joules or 1 calorie per gram degree Celsius. As for water, it takes a long time to heat up, long time to cool off. Water is used as a coolant, including nuclear power plants, which get very, very hot. All right, this is the first thing I want you to write down. This is the primary math you'll be doing for this unit. To calculate the heat, or if you want to figure out what the specific heat was for a substance, we use the equation Q equals mc delta T. M is in grams. Heat, or Q. The delta T is the change in temperature. The final temperature subtract the initial temperature. And so note, if something cools off, its final temperature would be lower than its initial temperature. Delta T therefore would be negative, therefore Q would be negative. So things that cool off, things that release heat would have negative Qs. Exothermic reactions have negative Qs. And then C is the specific heat, depending on the particular substance we are heating or cooling down. In general, we're either going to do it in joules per gram degree Celsius or calories per gram degree Celsius. And of course, we can go back and forth between them because 1 calorie little c calorie, is 4.2 joules. Well, it would change depending on what substance. It's C equals specific heat. So we're going to look at an example problem that's in the book to calculate C, the specific heat. The temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the copper absorbs 849 joules of heat. What is the specific heat of copper? So always a good approach in problems is list out your knowns and unknowns. We know the mass of the copper, 95.4 grams. We can determine the delta T, 48 minus the 25, or 23 degrees Celsius was the change in the temperature. Our Q is 849 joules. So when you see in a problem that they give you a number that's in joules or in calories, they're telling you the Q in that case. And one thing we don't know is the specific heat, the C of the copper. So we can take our equation, Q equals mc delta T, rearrange it for the C. So it's basically Q over the M and the delta T part. And then it's just a matter of plugging in our numbers. And we end up with 0.387 joules per gram degrees Celsius. So again, some hints here. When you see numbers in the problem, degrees Celsius, you are seeing the temperatures. Joules or calories, you are seeing Q. When you have joules per gram degree Celsius, which is right here, or you see calories per gram degree Celsius, then you're looking at a specific heat type problem. And note this 0.387, that's in line with the other metals we saw in that list, which had things down below 1. So this would be an example of finding the specific heat. You were told the amount that was absorbed, you were told the change in temperature, you were told the mass, you plug in the things you were told, and you solve for the one that was missing. Calorimetry is the measurement of heat into or out of a system for chemical and physical processes based on the fact that heat released equals heat absorbed. The device used to measure the absorption or the release of heat in a chemical or physical process is called a calorimeter. Foam cups are excellent heat insulators and are commonly used as simple calorimeters under constant pressure. They're also good because they're cheap. For systems at constant pressure, the heat content is the same as a property called enthalpy. We have seen the delta H's before, H for enthalpy of the system. Remember, we don't really measure heat so much as we measure changes due to changes in temperature. So here would be an example of a foam cup calorimeter. There's actually two foam cups. So the one is insulating the other. And then we have a solution inside in which we can measure any temperature changes that occur. Changes in enthalpy equal delta H. Q equals delta H. For our purposes, these terms will be used interchangeably in the textbook. Thus, you could have also said delta H equals MC delta T. And again, delta H or Q is negative for exothermic because, again, it's dependent on delta T. Exothermic, releasing heat, means it gets colder, so the final temperature would be less than the initial temperature. A negative delta T means a negative delta H or negative Q. Delta H is positive for endothermic reactions. Okay, here's a second problem that we're going to look at real quick. 25 milliliters of water containing 0.025 moles of hydrochloric acid at 25 degrees C is added to 25 milliliters of water containing 0.025 moles NaOH at 25 degrees C. In a foam cup calorimeter, a reaction occurs. Calculate the enthalpy change. That would also be calculate the heat in kilojoules during this reaction if the highest temperature observed is 32 degrees. So again, and I'd like you to write down this part again as an example of doing the math here, we would list the knowns and unknowns. You don't have to copy down the question itself. It is on page 513. But if we just look at the things that we know or don't know, they do tell us the specific heat of water, 4.18 joules per gram degree Celsius. We have a initial temperature, both waters are at 25 degrees. After the reaction, it gets up to a high of 32 degrees. Now, they also tell us, and sometimes it will do this for water, and we've seen this before, they told us there was 25 milliliters of water solution containing the hydrochloric and another 25 containing the base NaOH. So that's 50 milliliters of water. But for water, it's 1 gram per milliliter. So we can also say that we have 50 grams of water. We want to find out what the delta H is. This would be the same as also saying, what's the Q? Okay, Q equals delta H. So delta H or Q is going to equal MC delta T. Now, you might say, why do they have the negative sign here? Okay. What they're doing here is calculating the Q of the surroundings as opposed to of the system. Okay, and they have to be opposites basically. If the surroundings is getting warmer, then the system itself was losing heat. It was getting colder. If the system was getting warmer, then the surroundings were getting colder. So it has to be the same number, but one will be positive and the other will be negative. So the fact that they called this Q surroundings here, we have to put the negative sign here. So negative and then MC delta T. So again, this step was just to convert the milliliters into grams. You could skip that if you want. Just acknowledge that 50 milliliters of water is also 50 grams of water. Our change in temperature is 7 degrees. We went from 25 up to 32. And then we go ahead and plug it in. We have the 50 grams, the 4.18 joules per gram degree Celsius times the 7 degrees. We end up with 1,463 joules, which we divide by 1,000, and it becomes 1.5 or 1.463 if you're not rounding. Remember, the book always tends to round to the correct number of significant digits. If you're looking in the book for the answers at the back, they'll always be rounded. So negative 1.5 joules. Now, the surroundings, it was a negative 1.5 kilojoules. The system itself would have been a positive 1.5 kilojoules. They've always got to match. It's got to go somewhere. Here's a diagram to kind of illustrate the same idea for both exothermic and endothermic. You have your reactants, carbon and oxygen, to form product, CO2. The product is at a lower energy level than the reactants. 395 kilojoules are given off in this reaction. This would be exothermic. It has released heat as part of its process. Note, if we write it as part of the equation, the plus 395 kilojoules is on the right side. What we, in our equilibrium unit, would have said was an exothermic reaction in the forward direction. The products are lower in energy than the reactants. This energy is released. Delta H would be written as a negative. So, plus 395 on the right side can also be done as delta H equals negative 395 kJ. The negative sign does not mean negative energy, but instead means that the reaction itself produced, released, lost that energy to the surroundings. We can do the opposite for the endothermic. Now our reactant, calcium carbonate, which forms calcium oxide and carbon dioxide, absorbed some energy, so the products have more energy than the reactants. Note that the plus 176 kJ is on the left side this time, so it's on the left side for the endothermic reaction. Products are higher in energy than the reactants, thus the energy is absorbed. Delta H could also be written as a positive 176. So positive 176 here, or put it on the left side of the equation when it's included in the equation. An equation that includes energy is called a thermochemical equation. It's done in moles. And the main idea here is, if we forget about this part just for a moment and just think what we've been doing for months and months now, this 1 mole of methane, CH4, plus 2 moles of oxygen gas produce 1 mole of CO2 and 2 moles of water. In a thermochemical reaction, it also produced some heat. But the thing is, that is per 1 mole of CH4 that we would burn. This is in fact a combustion reaction, a CH compound burned in oxygen producing CO2 and water. So for every 1 mole of CH4 burned or combusted, we release 802.2 kilojoules. If we do not burn 1 mole, if say we only burned half a mole, then only half of the 802 would be released. And of course, we make 2 moles of water at the same time. The heat of a reaction is the heat change for the equation, exactly as written. The physical state of reactants and products must also be given. We have what are called standard conditions. Standard conditions are still 1 atmosphere, but 25 degrees, which is also considered room temp, not the same as STP, standard temperature and pressure. In that case, the pressure is still 1 atmosphere, but the temperature is 0 degrees. So there's a little bit of difference between standard conditions and standard temperature and pressure. So if you had a problem like this, you might want to write this one down. Again, we're just focusing on examples of the math here. If 10.3 grams of CH4 are burned completely, how much heat will be produced? Well, first off, we need to take that 10.3 grams and turn it into moles. And that's always a divide problem. So we take the 10.3, divide by the 16.05. 16 would be good enough as well. And then times the 802.2 that's in the equation, because that's done per mole. And we end up with 514 kilojoules would be produced. We are going to have a lab later on in which we actually burn some things to try to figure out how much heat is actually being produced. Not methane, but some things that are more edible. And again, if we put the 802.2 on the right side of our chemical equation, that would be the same as writing delta H with a negative sign, which means the heat is released for this reaction. When we burn things, heat is released. Okay, page 516, another example using the thermochemical equation. Calculate the amount of heat required to decompose 2.24 moles of Na8CO3. So they gave us an equation there in the middle there. And the thing is, we wanted to know to do the 2.24. That 129 again is per 2 moles. Okay, so we have 129 kilojoules, but it's 2 moles of Na8CO3 that's in the equation. So 129 per 2 moles. If we did a little quick division there, that gives us kind of the ratio of kilojoules per mole, and then times the 2.24, and we end up with 144 kilojoules. Enthalpy. The heat content of a substance has a given temperature and pressure, can't be measured directly because there is no set starting point. So basically, you have to measure changes. The reactants start with a heat content, the products end up with a heat content. What we measure are the changes. Again, we use the symbol H, and what we're looking for is the delta H. If the heat is released, the heat content of the products is lower. Again, delta H is negative, exothermic. If heat is absorbed, the heat content of the product is higher, delta H is positive. It's a repeat of what we've already seen. We've seen these diagrams before. Heat that is released or absorbed in a chemical reaction equivalent to the delta H. So here you see the 393.5 kJ. Notice that again, it's on the right. Delta H would be negative. important to indicate what physical state things are in. The G stand for gas. L's would be for liquid, S for solid. Notice that the delta H was a little bit different there for the H2O that was in a gas form versus the H2O that was in a liquid form. Heat from the reaction that completely burns 1 mole of a substance is the heat of combustion. And there is a table on 17.2 or 517, 17.2 is the table that can show you some examples. All right, now, a little bit different. Changes in state. Okay, and I want you to write this down because this is new from what we've been looking at. The molar heat of fusion, delta H FUS for fusion. The heat absorbed by 1 mole of a substance in melting from a solid to a liquid. Note the Q equation. There is no delta T in it. Basically, Q equals the mole times the delta H of fusion. The delta H of fusion will be some constant amount that would be provided for you, most likely in the problem, depending on what type of substance we were melting. But very important to note that when we have a change in state, when we are going from solids to liquids, and as you'll see, when we're going from liquids to gases, the delta T is not part of the equation. So this is very different from the Q equations that we were looking at before. There are values in table 17.3 on page 522. We also have heat of solidification. The heat lost when 1 mole of a liquid solidifies or freezes to a solid. And we can write that as Q equals MOL, mole, times delta H solid. Now, please understand, these are essentially the same thing. They're just going in opposite directions. So melting something or freezing something, those are just opposite aspects of the same process. So the numbers would be the same. It's just that in one direction it'd be positive and in the other direction it'd be negative. So essentially you could just see these as Q equals mass times delta H. That is because in some textbooks, instead of doing it per mole, they do it per gram. That's quite all right. Also note that the heat absorbed by a melting solid is equal to the heat lost when a liquid solidifies, just as I was saying. So the heat of fusion and the heat of solidification, the only difference between them is the negative sign. Okay? Now, remember, to melt had to absorb heat. It had to get warmer to melt. To freeze, it had to lose heat. So the reason that they don't show you any values for the heat of solidification is the only difference between the two would be a negative sign. So here's an example problem that you may just want to write down again as an example. How many grams of ice will melt if 2.25 kilojoules of heat are added? So we go back and look at our unknowns. We have the delta H, that would also be Q, 2.25 kilojoules. We notice we are given, or you might have to look up in the book if you were doing a problem out of the book, 6.01 kilojoules per mole. What we don't know is how much ice will melt. That's the question. How many grams of ice will melt? And even though this is done per mole, we could do it per gram if we just realized 18 grams of water per mole. And so here's our equation. We had solid water, ice, plus the 6.01. We're going to heat it up to produce liquid water. So here we change it from moles into grams because, of course, there's 18 grams per mole. So it's 18 grams per 6.01 kilojoules, 2.25 times the 18 divided by the 6.1. We can melt 6.74 grams of ice. Now, if we had just done 2.25 divided by the 6.01, that would have been how many moles of ice could be melted. Since the question wanted the grams part, we had to include the 18 grams per mole. Now, exactly the same thing can happen at vaporization. In other words, we have a delta H for vaporization going from a liquid to a vapor. No delta T again. So it's still Q equals the mass or moles times the delta H of vaporization. There's another table on page 522 for these particular delta H values. So we're going to have one heat of fusion going from solids to liquids, liquids to solids, and we have a heat of vaporization going from liquids to gases or condensation, gases to liquids. And again, the only difference between the two is the sign. Condensation is the opposite of vaporization or evaporation. Condensation is the opposite of evaporation. The molar heat of condensation is the amount of heat released when 1 mole of vapor condenses to a liquid. So remember, freezing and condensing, heat had to be released so that they got colder. Melting and evaporating, heat had to be absorbed. They had to get warmer so that they would melt or evaporate. And again, no temperature change when this is happening. Heat of vaporization is equal to the negative of the heat of condensation. And of course, because of this, this is why you can get such a scalding burn from steam, because the heat of condensation is being released. Just from going from a gas to a liquid. Okay, I'm going to skip this example. I want to go to this. So let's suppose we're going from -20 up to 120. Okay, so please note we've got some little dog legs here, if you will. All right, from -20 up to 0, we're going to use Q equals MC delta T. Okay, we're going to have a change in temperature. Then we have a phase change where it melts. Then it's just M times delta H. Then we have back to Q equals MC delta T, where we're heating the water. Then we have another phase change, where we're going now from liquid water to vapor. And again, Q equals the M times the delta H. And then finally, at the end there, we're back to Q equals MC delta T to figure out how much the gas is being heated. So to go from the solid to the gas phases, we have to use that Q equals mc delta T 3 times, but we have two places where we have a phase change where there is no change in the temperature at those points, and we just have to consider the given constants we would be given for delta H of fusion and delta H of vaporization. And just as a note, this can also happen when things dissolve. You can have a delta H of solution. Again, no temperature change, but heat can be released. Sodium hydroxide put in water. You can, in fact, feel the heat that is being released in this particular reaction. And all that's going on is it's breaking apart into sodium and hydroxide ions. The heat is released.